Across today's missile drawing boards and secret progress reports lie the shadows of coming events. Huge, populated satellites in orbit, manned rocket ships striking deep into space, exploring the interplanetary wilderness. During the next 10 years, the shadows will gather substance. But first, a workhorse vehicle is needed, a cargo freighter to carry enormous payloads of men and missiles. At the Redstone Arsenal near Huntsville, Alabama, a vehicle of this type is already under construction. Built by the Army Ballistic Missile Agency, it is known as the Saturn booster. Simultaneously, at the Rocketdyne plant in Canoga Park, California, power for Saturn is being developed. 8 of these rocket engines, arranged in a cluster, will give the Saturn 1.5 million pounds of thrust. During the first phase of Saturn engine development, 5 research and development engines for testing at Rocketdyne and 9 evaluation engines for the Army Ballistic Missile Agency will be produced. This effort is directed toward a static firing of 8 clustered engines anticipated for December 1959. Early in July 1958, the Army Ballistic Missile Agency informed Rocketdyne of the power requirements for Saturn, then known as Juno 5. At that time, the X-1, an advanced Jupiter-Thor design, was the company's most promising engine concept. The experimental X-1 offered many advantages: simplicity of design, reduced weight, economy, components available on a ready-made basis, reliability, components thoroughly proved in static and flight tests. Yet to meet cluster requirements, the X-1 was studied for even greater refinement. And gradually, a new concept, the H-1, emerged. The major H-1 characteristics were contributed by the S-3, S-4, and X-1 engine designs. The S-3 turbopump and thrust chamber were combined with the X-1 pressure ladder sequence, and the S-4 engine first proved the inclusion of turbopump and controls in the gimbaled mass. 2 other designs made important contributions. The MA-3 provided the combustor assembly, and the G-26 gave high-pressure ducts of the free bellows concept. These contributions, derived from long experience, have produced a greatly simplified engine. The S-3 has 68 major components. The H-1 has 10. If equipped like its ancestors, an H-1 would look like this. An elaborate starting sequence and its attendant mechanical auxiliaries have been eliminated by the turbine spinner. The fuel additive system for lubricating the turbopump does away with the oil tank and its complex control and pressurizing equipment. Electromechanical pressure switches, electrical relays, solenoid valves, provisions for pneumatic pressure have been eliminated by the pressure ladder sequence, which employs fuel pressure to open the main liquid oxygen and fuel valves. The gas generator blade valve was replaced by 2 poppet valves. The thrust control system was replaced by an orifice, and the pyrotechnic igniters were replaced by a hypergol ignition system. Requiring no hydraulic system and no pneumatic system, H-1 simplicity is evident. With gas generator and fuel manifold purges on, the engine is started by firing the turbine spinner cartridge. As hot gases from the cartridge expand, the turbine begins to spin, pumps accelerate, the main liquid oxygen valve begins to open. The sequence valve actuates, the main liquid oxygen valve reaches open position, and fuel igniter pressure bursts hypergol diaphragms. The igniter fuel flows, and initial combustion begins in the thrust chamber. At this point, the main fuel valve begins to open, instigating main propellant combustion in the thrust chamber. The gas generator liquid oxygen valve opens, the gas generator fuel valve opens, the gas generator ignites from the turbine spinner gases, the gas generator purge stops. Increased power is delivered to the turbine, and as the main fuel valve reaches the open position, pump speed increases to bring the engine into main stage operation. Another example of H-1 functional simplicity is the engine shutdown sequence. At the cutoff signal, the squib-actuated valves open and fuel pressure begins to close the main liquid oxygen valve. This reduces flow to the thrust chamber and gas generator. Consequently, the turbine inlet pressure drops, the pump decelerates, and fuel pump pressure drops. With the decay of fuel pump outlet pressure, the main fuel valve begins to close. By now, the main liquid oxygen valve is fully closed, and all pressures continue to drop. Thrust decays to zero, and the main fuel valve reaches the closed position. A comparison of electrical systems offers another example of H-1 simplicity. Ancestral circuitry was, to say the least, large in concept. Due to the pressure ladder sequence, the H-1 electrical system is more simply conceived. With the December 1959 deadline to meet, ABMA has encouraged fast action in developing Saturn power. The design proposal won a contract in September 1958. By the end of May 1959, all 5 research and development engines had undergone testing, and 2 evaluation engines had been shipped to ABMA. The first R&D engine had completed a full stand duration test by December 31st, 1958. The second R&D engine underwent 40 stand duration tests in less than 30 days. A total of 52 tests were conducted with this engine for a cumulative duration of 1,966 seconds. Representing a deliverable configuration, the third engine was tested in early March. The main test objectives were gimbaling, gain and system pressure drop studies, and starting the engine in a canted position. On April 3rd, a successful H-1 shakedown test was performed with the fourth engine in the series of 5 research and development engines, checking out acceptance test stand tree 3A and aspirator evaluation. The fifth engine in the research and development series was installed for testing 11 May. By June 12, 27 stand duration tests had been performed on this engine with an accumulated test time of 1,338 seconds. The fast action progress of H-1 development is due in large part to the cooperative attitude shown by Rocketdyne and ABMA personnel. Here, ABMA representatives attending a product improvement conference at Rocketdyne gained technical information from the first full-scale engine mock-up. And top management personnel from both groups examined the first deliverable H-1 in the company's engineering lab and witnessed the gimbaling of an H-1 during a hot fire test. Product improvement conferences, technical consultations, the free exchange of ideas and know-how have helped keep the program working smoothly on schedule. An outstanding feature of the H-1 engine is the reliability of its components, reliability which is due in large part to countless laboratory tests on progenitor types. For example, laboratory studies of hypergolic ignition have been conducted in numerous tests. Here, the time delay characteristics of various pyrophoric fluids are tested with liquid oxygen. These studies are directed toward smoother, faster ignition performance. Similar studies are underway to test hypergol reaction at various altitudes. Reliability is further promoted in the laboratory by unrelenting inspection methods. The inspection of gimbal bearings demonstrates this work. Using a height gauge, the gimbal cross is checked to determine the concentricity of all diameters and that all surfaces are parallel. Years of experience with predecessor components lie behind each H-1 part and system. Another important laboratory activity is the simulation of launch and flight environments. On this machine, representative gimbal bearings can be subjected to loads exceeding those experienced during actual missile launch. A maximum thrust of 250,000 pounds can be applied. Bearings are tested in both pitch and yaw positions, and a torque force may be applied as desired. At the Army Ballistic Missile Agency, each evaluation engine undergoes static firing tests similar to those conducted at Rocketdyne. This is done to evaluate the various missile systems associated with the engine, to indoctrinate test personnel, and to obtain sea level reduction data at the Alabama test site for correlation with the data gathered at Rocketdyne's California site. When the evaluation program has been completed, 8 engines will be clustered and test fired on Static Test Tower East, the gigantic captive missile test stand now being enlarged to accommodate the Saturn cluster. As of August 1st, 1959, all schedules and objectives of first phase development show a favorable status. The 5 engines built for research and development testing are in continual use, proving design modifications and system reliability. 3 evaluation engines have been delivered to ABMA. 11 runs have been made with these engines for a total firing time of 1,126 seconds without serious malfunction or delay. The H-1 engine now stands as a tested and proved design ready for its ultimate use. Power for Saturn.